All right, well, thank you, and thanks for the invitation to come and present. So I'm going to give a really aura-centric view of stratospheric water vapor in the TTL and talk about how aura has advanced our understanding of this. Let's see if this works. Oh, it does. All right, so here's a schematic of what we're talking about. So the TTL, tropical tropopause layer, is this layer between the troposphere and the stratosphere, and it's this transition. The tropopause is right in the middle of it. And I'm not going to talk about the monsoons, not in 15 minutes, so this is really going to be focused on the tropics. And so the processes that are occurring here set the water vapor in the stratosphere. That's important for things like climate and for things like atmospheric chemistry. And so let's talk about what are the processes that are going on there. So this is a schematic of the TTL. And so it goes from about 14.5 to about 19 kilometers. That's the potential temperature. And essentially air enters a TTL by convection, because that's the only way you can get it up there. And once it's in the TTL, TTL air is radiatively heating, so it rises. So it rises through the TTL, and it goes across, the colors here are temperature, so it's kind of warm here, and it's warm here, relatively speaking. And then it's cold right here at the tropopause. And so it traverses this cold region as it travels through from the bottom of the TTL where it detrains into the stratosphere. And when it does that, it forms clouds. It hits really cold temperatures, and it generates clouds. And then the clouds sediment out. They fall out, and that takes water vapor out of the TTL. And then when the air enters the stratosphere, it's essentially gone through a cold track. And so it's very dry. And then the other process that's important is convection. So you can not only have air detraining at the bottom of the TTL, but you can also have convection getting too close to the cold point. If it gets above the cold point, then you're no longer being regulated by the temperature minimum. You're actually getting into the stratosphere. And we know that happens. And really the question is, how often does it happen? Where does it happen? How important is it? So I'll cover that a little bit in a second. So I like to think about, at least when I was preparing the talk, I was sort of segmenting aura's advances into 3 different categories. First, large-scale temperatures and transport, how that regulates water vapor, microphysics, and unresolved temperature fluctuation and convection. So I'll talk about these each in turn. So let's start off with large-scale temperatures and transports. So it was understood even before aura that the stratosphere, in fact, goes all the way back to Brewer. Brewer is the one who really understood that the water vapor in the stratosphere was set by the large-scale temperature of the tropopause. And so a lot of the analyses that were done compare stratospheric water vapor to the temperatures, the minimum temperature in the TTL. And so, for example, lots of people have run trajectory calculations. Mark Schilber and I have run probably tens of billions of trajectories if you integrate over the last 10 years. And essentially what they do is, whenever you do a calculation like this, you have to make some assumption about the microphysics. And so we're going to make the assumption that many people do, that you have instant dehydration. Whenever you hit saturation or some relative humidity threshold, you instantly lose all the additional water. And so that sounds kind of unrealistic, but as I'll show you, it does remarkably well. And what that means, though, is that when you get to the stratosphere, the water vapor in the stratosphere is set essentially solely by the coldest point it sees. So they call that, some people call it Lagrangian cold point or Lagrangian dry point. So all you need to do then is launch tens of millions of trajectories, use reanalysis to advect them through the TTL, figure out the coldest temperature they see, and then that determines the water vapor that makes it into the stratosphere. And so I'll show you how well it does. This is some MLS data. So it's tropical, 100 millibar, tropical average, 100 millibar monthly data. And you can see it looks, has a lot of bumps to it. And so if we run our trajectory calculation, it only looks at the minimum temperature. It does a fabulous job. I mean, it does, if you were going to make up data, you probably wouldn't make it look that good. And so this really, and the correlation coefficients are in the 0.9, 0.93, 0.97. So it really says that we understand what's causing these interannual variations in water vapor. They're caused by variability in temperature. But we can actually go a step, I should say first, and then a lot of the power of aura really also, when it comes to water vapor, comes from looking back in time. So you can connect the halo data from URs to the Aura data. This is a plot that came out recently, Randall and Park. And so these light gray symbols are, not Sage, Halo. And the dark symbols are MLS. And the blue line is what you'd predict just from radiosondes. If you took the coldest temperature that radiosondes measure and you average it. And you get a correlation coefficient that's a little less than we do with the trajectory model, which says that adding the dynamics that the trajectory model has, because actually using reanalysis wins, probably adds a little bit of information. But you do quite well if you just say, what's the average temperature of the tropopause? Again, this goes back to Brewer. I mean, he's really the first person to do that. But we can actually go a step further in this. So it's not just we can say the temperature, but we can actually assign these bumps and wiggles to actual processes. So the processes are important. Things like the QBO. So as the QBO descends into the TTL, it affects the temperature. So if you affect the temperature of the TTL, you're going to affect water vapor coming out. The Brewer-Dobbs circulation. If you have a stronger or weaker Brewer-Dobbs circulation, a stronger Brewer-Dobbs circulation increases upwelling. That tends to cool the TTL. That tends to reduce water vapor going up. And then a warming troposphere also tends to warm the TTL region. So all of these things can affect stratospheric water vapor. And so we can actually, something that I did a couple years ago is we can actually model the water vapor in the stratosphere, in the lower stratosphere, as a multiple linear regression of QBO, Brewer-Dobbs circulation, and tropospheric temperature. And then we just use regressors, typical regressors, and you can get an incredibly good fit. So the black lines, this is time going back to 1980. The black line is actually a simulation from a trajectory model, but as I showed you before, the trajectory models reproduce the data almost exactly. And if you actually do this with data, at least for the MLS period, it looks almost this good. And then the blue line is the fit. And so you can see that we can actually assign, we can explain all of these bumps and wiggles. One thing you might want to note, the one place the fit doesn't do that well is right after the volcanoes. So it tells you the volcanoes are having an impact on stratospheric humidity. And so we'll say we can actually look at this now. We can actually say, well, what's causing this bump right here? And so we can say, okay, it's the QBO combined with a little bit of an effect from Brewer-Dobson and a little bit of temperature. So these are the actual components of the fit. So we can actually quantitatively figure out exactly what's driving the variability in stratospheric water vapor. Now you might look at this and say, well, we've solved stratospheric water vapor, but there are actually still some unresolved issues. And you need to go one level down into microphysics to understand that. So this is a plot that I adapted from a paper Mark Schobel wrote, 2015. So this is water vapor, and this is Calliope cloud fraction in TTL. And this is where the observations are. Okay, so the observations of this oval, about 4.6 ppm of water and cloud fraction. Now, if you take our instant, what we call the instant dehydration model, the model that just sets water vapor purely as the minimum temperature it sees, this is what you would predict the amount of water vapor is. And those models don't really make a prediction of cloud fraction, so I just put a line there. And it's about 3.2, so we've got a problem. So the instant dehydration model does really well looking at variability, but it doesn't predict the right amount. And that's because we've neglected microphysics. And so what Mark did is he married our trajectory model to actually a cloud model that he developed, I think, with Eric Jensen and Stefan Fuglerstaller. And if you put realistic microphysics in, you can actually get both the water vapor and the cloud fraction right. And so again, this is the observations. These symbols are different nucleation relative humidities. So he's changing the nucleation relative humidity, sort of reasonable values. And you can see that you get about the right water vapor. And you also get about the right cloud fraction. And this is consistent with Uyama estimated that microphysics added about 0.7 ppm at 100. So we see this. We see about a little more than that in this paper. And then Eric Jensen's PNAS paper where he looked at the global Hawk data, you see supersaturation all the time. So this is not at all unreasonable. And we can also look at gravity waves, or these are unresolved, I guess I should change to the other side. So this is unresolved waves in the reanalysis. The reanalysis, because of its finite resolution, can't resolve every wave. And so we can put in additional waves into the temperature field to see if that is a big problem. And so we're using a nucleation relative humidity 135. And you see that the unresolved waves actually don't have a big effect on the amount of water vapor. They do have a big effect on the amount of clouds. And I'm not going to talk about it here, but clouds give you this orthogonal axis for you to understand what's going on in the TTL in addition to water vapor. Overall, we have a reasonably good, I should say this is in agreement with other papers that have come out on this. We have a reasonably good understanding, but there's still more things going on. Somebody's talked in the last 4 minutes about convection. So if you look at this plot, this is the same plot I showed a second ago, you don't see a lot of room for convection because we can explain the amount of water vapor with microphysics plus large-scale temperatures and transport. So at most, you'd get a few, you could imagine a few tenths of a ppm, which is probably about right. And Mark actually estimated in this paper that average over the bulk stratosphere, convection only added a few percent at most. And Uyama et al., 2018, they estimated convection at 100 millibars increased water vapor by 15% during the summer. You might say, well, those aren't consistent, but I think they are consistent because Mark's paper was looking at the bulk of the stratosphere, and Ray's paper was looking at 100 millibars. And there is quite a bit of dehydration that goes on above 100 millibars. So you can imagine that convection could be adding a lot of water at 100, but that doesn't actually make it into the stratosphere. And so I'm going to go over a little, and then this plot right here also shows you there's just not a lot of room left over for interannual variability in convection. There's just no room for it. I mean, you can explain everything with just temperatures. And I would just give a shout out to my former grad student, Hao Yi, who actually analyzed this. And he found, and I believe it's right, that there is a very small but detectable amount of convection variability in the signal. But read his paper if you want to see it. I'm not going to talk more about it. But I do want to end this in the last 2 minutes and just to show you some work that we've been doing looking at convection on the seasonal cycle. And what we're trying to do, so this is MLS data, this is month, and this is latitude. And so you can see the seasonal cycle. This is essentially the tape recorders. You go here, you have low values in DJF, and you have high values during Northern Hemisphere summer. And you can kind of see there's some structure to it. It's not sort of located right over the equator. But you see this bimodal distribution. And I'm going to call this the asymmetry. The fact is you have a much bigger summertime maximum in the Northern Hemisphere than you do in the Southern Hemisphere. And so when I refer to the asymmetry, this is what I'm talking about. Now, what's interesting is, you remember our trajectory model did a fantastic job reproducing interannual variability. If you ask it to reproduce a seasonal cycle, it does not do a very good job. It does not reproduce this asymmetry right here. And what it's doing is, this pattern reflects the fact that the temperatures are symmetric about the equator. There's no asymmetry in temperatures. So this has to be something other than temperature. And we've tried microphysics. We don't see that microphysics can explain this. And so really, it's convection. And that's the obvious last person standing. As Sherlock Holmes says, once you eliminate all the other suspects, what you're left with has to be the guilty party. And so we know there's a lot of convection detraining down here at 14 kilometers, right above the bottom of the TTL. But if you can get convection up above or even near the cold point, then some of that water can leak through, and it won't be controlled by temperature in that case. Now, the problem with what makes it so hard to add convection is you have to get the altitude right. If your altitude is a little bit wrong, in particular if it's low, then your model will not simulate any effect of convection. So some people, previous investigators have tried to put convection in. Mark has a paper, Ray Uyama has a paper, but we're going to try something different, sort of a different approach. And that is to basically you do a perfect model experiment. And essentially, these are the plots I showed before. And this is the GSCCM at 100 millibars. And this is exactly, you can see the GSCCM reproduces this exactly. And interestingly, if we take the meteorology from the GSCCM, we run it through our standard trajectory model, we also get exactly the same thing. So I would argue that whatever's going on here is probably what's going on in the real atmosphere. And so what we think is happening here is convection. And the advantage of using the model is that the model has we can get the actual perfect convective fields out of the model. And when we put those in the trajectory model, this is what it looks like. And you can see this looks just like this. So we can solve the problem here by adding convection. And the argument we make is perhaps you can argue it's a circumstantial case, but it's a strong circumstantial case, especially in the absence of another hypothesis that we really see the effects of convection in the northern hemisphere during the summertime. So I'll wrap up at this point. 30 seconds over, sorry. So Aura's measurements have greatly improved our understanding of the TTL, and large-scale temperature and transport are the primary regulator of stratospheric humidity. But microphysics is important. It can increase humidity by, say, a ppm. Convection doesn't look to be too important, except regionally, it does appear to be important. So, for example, if you have something like the Anderson hypothesis that increases in water vapor can lead to ozone depletion. I'm not endorsing that, but those are the kinds of things that could be true if convection is regionally important, as it appears to be in the seasonal cycle. And I'll wrap up. Thanks. Thanks for sticking around.